Okay, time for the last step, and that is to simply extrude the thickness of these closed curves to create the actual structure. Um, so, unfortunately, you know probably in Rhino that you can extrude the surface, and in those options to extrude the surface, you can cap it kind of all in the same operation. Unfortunately, in Grasshopper, it doesn't quite work that smoothly. We have to do it as individual operations, so it takes a couple more steps, but again, it's not too difficult, and you get to learn a little something extra from it. So the first step we need to do is to actually bring down the closed curves from the previous step, and I've already done that. Again, you guys should know how to do that already, but you go underneath parameters, geometry, and these are just simply curves, and wire those in and make those wireless receivers and bring them down below. I've simply labeled them as closed first set, which is the one closest to the x-axis, and closed second set, which is essentially the mirrored version of itself. So to do this now, what we want to do is split the surface that is within each of these closed curves from the barrel vault surface as a whole. So in order to do that, we need the barrel vault surface. We have that from way up above. So if you go to very first step, that would be our target surface. So let's copy and paste that. Remember, anytime you copy and paste something that has a Rhino object directly tied into it, you always want to piggyback it and make that a wireless receiver. That way, in case you ever change the original, the one is tethered to it, and it will automatically update as well. So bring that down below. And we're going to go ahead and kind of use that for both of these. So what we want to do is simply use a split surface command. Let's come underneath our intersect, and we're intersecting physical because we're intersecting curves with the surface, and it's simply called split surface here. We're going to do this twice. We're going to do it once for the first object and once for the second object. The surface is always the same, but the curves are going to be what are different. So we'll split the first curve and split the second curve. Let's turn off all this previous information, and you should get two trimmed surfaces for each of these. The two different trimmed surfaces are the surface within the closed curve and all the rest. Second operation, surface in the closed curve, and all the rest. To isolate this, we want to keep one of those and eliminate the other one. Again, let me just kind of show you what these both look like. One is, they're both trimmed surfaces. One is the inside area and one's the outside area. Okay, and because we did this as two separate operations, it essentially did it twice, i.e. as if there were two separate barrel vaults that it trimmed from as two separate operations. I don't know which of these we want, whether we want the first or the second. I don't know if the 0 index is the inside and the 1 is the outside, or vice versa. So we'll do a little trial and error. We're going to go, anytime we want to keep one and not the other, we're going to go to list item. Okay. And we're going to run the surfaces in as our list, and we're going to turn off the preview. And actually you can see here, let's turn off the second set just to help us. You'll see that by default the list item is set for 0, and it looks like it's actually keeping everything except for our surface. So we probably actually want list item 1. So we're going to go to parameters, drop in a panel tool, put a value of 1 in there for one index item 1. And there it is. So there we want index number 1, and that's the surface area inside of the closed curve. And we're going to go ahead and copy and paste that. Okay. And we're going to use the same panel tool. Hopefully it's the same for both of these, and it is. Good. Okay, so now we've gone ahead and kept the inside surface for each of those closed curves. And again, now that we have surfaces, you guys all hopefully know in Grasshopper, or in Rhino, excuse me, there's an offset surface component. There's the same exact option inside of Grasshopper as well. So to do that, what we want to do is actually do an offset surface, which I'm actually having a hard time finding, but there it is. Okay, it can be found underneath our simple surface, utility, and offset surface, or just offset in this option because it's already underneath the surface category. We're going to do both of these, and you'll see that they both require a distance. So I'm just going to do a simple number slider and say a minimum distance of 0.1 is less than a value of 1 is less than a value of 2. There we go. So there's my, I'm going to relabel this as offset distance or structure depth. Okay, and run that into the D input, which is the distance input of both of my offsets, and run my two surfaces into each of the S inputs, the surface inputs. And there you go. So now you get a offsetted version of each of those surfaces on the inside. And I'm just going to go ahead and hide this object in Rhino for right now. Obviously it still exists, but you can see there are the two versions of it. Essentially those are the two kind of edge surfaces of these. So now when we, what we need to actually do now is to create the perimeter of each of these. And basically what we need to do is, again, find the perimeter edges, okay, and loft these together. So we'll loft the edge of the first surface, the edge of its offsetted version, the edge of the second, so on and so on. Well, we already have the edges of the first. Those are the closed profile shapes. So we're going to copy and paste these guys once again. The closed curve first set and closed second set. Let's go ahead and for a moment just group all this stuff because we kind of did a nice little operation there, and we can annotate that as a set. And we have the second set here also, okay? And these are the boundary curves around the surface. Now we need to find the boundary curves along their offsetted versions also. You can see these lines, but those lines are really just the edges of the surface. If we turn off the surfaces, those lines disappear as well. So to find the edges, preview on. To find the edges of these surfaces, what we're going to do is go to Surface, Analysis, and we're going to go to BREP Wireframe. And what BREP Wireframe does is it gives us the individual wireframes or the wired edges of these surfaces. Now if we go ahead and drop a panel tool in here, we can kind of look at these real quick. And you'll see what it actually does for us is it's broken it back into 4 individual curves. Again, we want them to be closed curves, one continuous closed curve, like our original was. So to do that, we simply want to join these. So go to Curve, Utility, and Join Curves. We're going to do these both simultaneously. Whoop. All right. And now we're back into having one closed curve. All right. And easy enough, we can go ahead and loft these together. So again, we're going to go underneath Surface. We're going to Freeform. We're going to go to Loft. And we're going to loft the first set with the second set. And you'll notice you're like, oh, well, why didn't anything happen? Okay. Again, lofting is very much dependent upon data structure. So if we kind of take a peek at our data structure, we'll see that we have 0, 0 as the tree branching. And in this data structure, we have 0, 0, 0, 0. Okay. From the previous steps way back up above here, we had an issue with data structure, and we used this whole path mapper to get to the same data structure. And I told you we could use simplify, and that worked out pretty well. And again, here's another case where we can actually just simplify. So if I right click on the input and simplify, it'll simplify everything coming in. And that should go ahead and allow for our mapping to take place. Let me go ahead and let's do these, rewire these, because that didn't seem to work the way I was anticipating. And now let's go ahead and, having slight issue. Let's go ahead and do this. Let's delete this loft. Let's go ahead and go underneath another surface. Go to Freeform. And I'm going to go ahead and loft is right there. Let's take a look at this data. Okay. What if we simply, let's flatten this. Okay, there we got 0 data structure there. And I'm going to go ahead and flatten this one. Good. And now let's go ahead and loft these together. There we go. Okay. So the simplify didn't work so well, but the flattening did, because again, it simply put the same path structure on there. That seemed to work out perfectly well. And there we go. But again, now what we have is 2 faces as well as individual edges. We still don't technically have one continuous closed BREP. We've got, let me just turn off all this previous information. You'll notice that this lofted one actually has no faces to it. You can see right through it. Okay, so we need to join all of these individual surfaces to create one continuous closed BREP. So we need our offsetted surface as well as our original split surface, which is right here. So we're going to go underneath parameters, we're going to go geometry and surface. And we're going to call this our structure A surface. And then we're going to do the same thing for our offsetted structure A surface. This is our offset structure A surface. Make these both wireless receivers. You could leave them because they're technically in the same step and it's not a big deal, but let's just go ahead and bring them both over. And we're going to combine all this stuff into a single joined B-rep. Okay, so underneath our join options, we have a B-rep join. If you're looking for it, it can be found underneath our surface utility and join B-rep. All right, so we're going to go ahead and drop in one of those. And again, let's just flatten everything to make life simple coming into it and merge all these together. And turn off some of this old information. And with any luck, we have one closed, locally defined B-rep. That's the big thing. We want to make sure if we don't flatten those, we might not get one closed B-rep. So be sure you flatten those. Again, let's go ahead and just copy all this information. You want your flattened second set, which is coming from here. As well as our joined, remember to flatten it. There we go. Okay, so now it's working on our second set here. Okay, and then last but not least, that's our second set. Good. We want these not coming from our A, but we want these coming from our B's. So we're going to relabel this as B. And this is the offsetted version of B. All right. And we want to make sure that everything is in the same data structure. So we want to make sure we flatten this as well. And there we go. And last but not least, check to make sure the result is one closed B-rep. Okay. And we'll group all this stuff together, and it's pretty much the same step, just mirrored, so you only need to annotate one of those. But that's how we go ahead and create the depth to the structure itself. And again, we can go back up a couple steps and turn back on our lofted onion domes. There we go. And you can start to see we have one bay with the onion domes that works all the way through. Now, for kind of the next steps, if you would, what I would encourage you to do is a couple different tasks. One task would be, how do I repeat this, right? Remember, so if I go ahead and show my vault, we may want this to populate the entire length of the vault, not just to create one individual bay, but how do I repeat this? The second operation in there is, you'll notice that the every other bay is different, because where we hit on the positive, we get a negative void for where the next onion dome is. So you'll actually need to create a mirrored version again and create an A-B pattern to kind of continue all the way through. So, and the last trick is, does this work on other shapes? Does it always have to be a barrel vaulted dome, or can it be some other form? In particular, this is a project by Shigura Ban, which is, it looks kind of like a pea pod, but it's the paper pavilion. I believe I probably have an image or two I can share with you. Here we go. Here's the kind of geometry structure. Here's the actual paper vault, but you can see that the form goes in and out, and it's got this kind of diagrid paper structure within it. So can this same logic be applied to some other form that isn't necessarily just a straight extruded vault? So, all right, best of luck. Let me know if you have any issues, and we will pick up on class again next week, Monday. Thank you much.